Let's face it, packing for a big trip is always tough. But what if you were packing rare, perfectly pure germanium crystals to study dark matter all the way on the other side of the world? You would need to package them up in a lead box and slowly ship them in the bottom of a boat across the ocean. Then load them on a truck, carefully transport them across the US, and avoid the mountains on your way to California, if you were serious about protecting them from cosmic rays. This is baby SLAC.
They call this In Station 3, or HEPL, the Hansen Experimental Physics Laboratories.
It's the original accelerator on Stanford's main campus. In the late 1950s, this experiment paved the way for the 2-mile-long accelerator at SLAC. But today, this underground bunker is used to shield the perfect crystals that are being polished for the SuperCDMS dark matter experiment.
Hi, my name is Joseph Garvey. The crystals at the very end will become the actual detectors that find dark matter. They will have circuitry put on them, they'll be put in a housing, and they'll go deep underground to shield it from all the outside cosmic rays and everything. It's a single crystal, so every atom in this crystal is arranged perfectly. So it's like an infinite scaffolding. And so that way, vibrations travel very well through it. So the idea is we put it deep underground, we hide it from everything that might disturb it, we get it really, really, really cold. 0.03 on the 0 scale, negative 460 plus degrees. And so at that point, atoms, which are normally moving, are kind of sitting still. So when dark matter comes by, it hits one of these atoms and it vibrates. And that vibration gets carried through this scaffolding a lot better than it would if it wasn't arranged. And so eventually this vibration, which causes more and more vibrations, hits the surface where we have our detectors, our sensors, and we can read out that very, very small signal because of how we've protected it and shielded it, what this effectively is for us, the dirt above us. As the particles come, they, hit you on the surface, but then they have so much more stuff to go through where they might run into things, deposit energy here, deposit energy there, stop before they hit the actual crystal and put their energy into the crystal, which we don't want. The idea of polishing is almost like running a finish line, but wanting to barely come up to the finish line and never finish without ever crossing it, So you start off getting most of the race done, go as fast as possible. I'll use a very heavy grit, like a rough sandpaper, and I get it to where it's generally flat, and then after a certain point, I'll use a finer level, slow down a little bit, slow down a little bit, slow down a little bit. So you just keep going finer and finer levels using different slurries. You use different types of pads, different sandpaper levels essentially. And then when you're done with that first step, it looks like a mirror, it looks fine. You look at it under the microscope and you can't see a patch anywhere that doesn't have a scratch going across it. It's usually like hundreds of scratches in your view. And you reduce it to 5 and then 2, and then all of a sudden you spend 15 minutes at a time scanning the entire crystal because you got to make sure there's nothing there. Back and forth, and then you get that one, your nemesis. You got to fight that one scratch forever because it's the last one and you got to get rid of it. Until finally you have not only the shape that you want, but no defects, no scratches, no pits, no chips. You want a perfect mirror shine golden rule surface. Your phones, your cameras, everything else, these little microcircuits. And the next step, we do photolithography to lay down little microcircuits, all of our sensors on the surface. And so whereas we want complete 100% scratch-free, defect-free, pit-free surface, industry just really wants like 90% yield because they're just cutting up all these little circuits and selling the separate pieces across a giant wafer. So we need it 100% clean so we don't have any shorted channels or anything like that. No one wants to go to the levels that we go to, I guess.